When we learned the node voltage analysis previously, we used this example. Check it out. Besides the resistors, there are only independent current sources in the branches. Actually, this case is the simplest for writing the node voltage equations. But for real circuits, they would be more complicated than this case. Next, we will learn the methods for some special branches. The first special case is the branches of the current source in series with a resistor, such as this branch. Then how to deal with this branch when we write the node voltage equations. We've already known that the node voltage analysis is essentially a set of KCL equations. So we can start from the initial KCL equations. Write the KCL equation for node 1. The current through this branch should be expressed as UN1 minus US1 over R1. And the other branches are exactly the same as what we've learned before. The branches connected to node 2 have no change, so the equation should be the same as before. Now we rewrite this equation, that is, move all the items without UN1 or UN2 to the right part. Now we find that there is an additional item, US1 over R1 on the right side. This is actually a equivalent current source. We conduct a equivalent transform of the voltage source in series with a resistor in the original circuit. Then we can get the additional equivalent current source item on the right side. By the equivalent transform, we can see that the resistor is still R1. While there is an equivalent current source here, note that the reference direction of the current source should be upward and its value should be US1 over R1. After the transformation, we can see that it is exactly the same as the original simple circuit. All the branches in the circuit are either resistors or current sources. Okay, this is the first special case. That's all for it. Now look at the second case, that is, branches consisting of the independent voltage source. Take this circuit as an example. We all know that the node voltage analysis is essentially a set of KCL equations. That is to say, we need to express the currents through each branch in terms of the node voltages. But for such a branch with pure voltage source, according to the characteristics of the ideal voltage source we've learned before, its current is determined by the external circuit and cannot be expressed by its voltages or the voltage difference between these two nodes. So when forming the node voltage equations, we need to use this special method. We might assume that the current flowing through this branch is I. Then we can write the node voltage equations. For node 1, its self-conductance is G1 plus G2. That is G1 plus G2 times U1. While for the coefficient of node 2, it should be the mutual conductance with node 1. It is minus G1 times U2. There's no resistor branch directly connected between node 1 and node 3, so their mutual conductance is 0. On the right side, it should be the sum of all the current sources flowing into the node. In this circuit, there's no current source directly flows into node 1, but if you write 0 here, you are wrong. All these items on the left side only involve branches G1 and G2, but no current through the branch US. If you write 0 in this KCL equation, that is certainly wrong. We might regard I as the source current flowing out of the node, so it should be minus I on the right side. Well, next we write the equations for node 2. It's simple due to all the pure resistors branches connected to node 2. So its node voltage equation should be like this. The mutual conductance with node 1 is minus G1. The self-conductance G1 plus G3 plus G4, and the mutual conductance with node 3 is minus G4. On the right side, the sum of the current source flowing into node 2 is 0. Similarly, we can write equations for node 3. There is no resistor branch directly connected between node 3 and node 1, so the mutual conductance is 0. The mutual conductance between node 2 is minus G4 times U2, and the self-conductance of node 3 is G4 plus G5. It should be G4 plus G5 times U3. On the right side, the sum of the current sources flowing into node 3 here should be I. By now, the current can't be solved. Because we have 3 equations but 4 unknown variables, in addition to U3, U1, and U2, there is a new variable I. So we must find a new equation to solve the circuit with 4 equations and 4 unknowns. What's the new equation we should look for? Look at the branch US. Its element characteristics has not been used yet. That is to say, in the circuit, no matter how the voltages and the currents of the other branches change, the voltage difference between node 1 and node 3 should be equal to US. So we can add a supplementary equation regarding the relationship between the node voltages and the voltage source. It should be U1 minus U3 equals US. Solving these 4 equations with 4 unknowns, we can solve the circuit. In fact, for the circuit containing only one independent voltage source, we can take another simpler way to solve it. When we wrote the node voltage equations for the circuit just now, this node is selected as a reference node, but we know that the reference node can be selected arbitrarily. So we can select another more appropriate node as a reference node, such as the node below. Now we can see the voltage of node 1 can be obtained immediately, that is U1 equals US. The node voltage equations for node 2 and node 3 are relatively easier because the branches connected to node 2 and node 3 are all pure resistive branches. It should be pointed out that this method is only applicable to the circuit containing one independent voltage source. If there are 2 or more independent voltage sources in the circuit, this method cannot provide any superiority. For example, if between node 2 and node 3, there is another branch of a voltage source US2. Now, if we still choose this node as a reference node, we can determine the voltage of node 1 only. While writing the KCL equations for the node voltage equations for node 2 and node 3, we still have no way to express a current of the branch US2 in terms of the node voltages. So we still have to use the method learned previously. The variable I, that is the current of the branch, should be assumed. Correspondingly, the additional equation is required. That is the relationship between the voltages of node 2 and node 3 and the independent voltage source. Well, this is a second special case, that is how to solve the circuit with pure voltage source branches. The third case is a circuit containing the dependent sources. For example, in this circuit, there is a voltage-controlled current source, VCVS. How to write its node voltage equations? The first step, we consider the VCVS as an independent source. We don't regard it as a VCVS, but an independent current source. We first select a reference node before writing the equations and label the node voltages for the rest of the independent nodes. Then we can write the equations for the circuit. We can see the self-conductance of UNY should be 1 over R1 plus 1 over R2. That is 1 over R1 plus 1 over R2 times UN1. The mutual conductance with node 2 is minus 1 over R2, that is minus 1 over R2 times UN2. On the right side, it should be the sum of all the current sources flowing into the node. It is IS1. For node 2, its mutual conductance with node 1 is also minus 1 over R2, that is minus 1 over R2 times UN1, while its self-conductance is 1 over R2 plus 1 over R3, that is 1 over R2 plus 1 over R3 times UN2. On the right side, we should note that we treat the dependent source as independent source in this step, so the sum of all the current sources flowing into node 2 should be GU. By now, the equations are not completed because we have two equations with three unknowns. In addition to UN1 and UN2, there is one more controlling variable, U. So we have to find a new equation to solve the circuit. Because the node voltage analysis is the method writing equations in terms of the node voltages, all other variables in the circuit should be expressed in terms of the node voltages. So the new equation we are looking for, in fact, is the variable U expressed by the node voltages. In the circuit, the controlling variable U is here. Express it in terms of the node voltages. It should be U equals UN1 minus UN2. Okay, three equations with three unknowns. We can solve the circuits. Please think it over. If it is not a dependent current source here, but a dependent voltage source, how shall we deal with it?